I know it's kind of late, and it's kind of last round of the talk, so I tried to go without putting too much details, otherwise then people just like sleep and go away. But I'm going to try to give an overall about the Ubuntu Touch project. My name is Ricardo Salveti. I'm one of the main developers of the foundations for the phone and tablet. And I've been working like for Canonical for 4 years already. I was allocated for a few years in Lenaro doing the work on the platform and the developer platform team, and moved it back to Canonical to kind of bootstrap the Touch project because I thought it was like a pretty interesting concept and something that I was planning on doing. That I was trying to do kind of somehow in Lenaro, but kind of looking in a different approach in here and try to do something beautiful at the same time. So kind of the agenda, I'm going to give some of the background on the project, why did I decide to start it, some of the challenges that we had along until now. We didn't yet release a product in the market. We do have everything, all the development is open source, and we do have some compatible devices that you can grab images and flash and use. But there's still no official device yet. There's 2 vendors that we are partnering at this point, which is BQ and Mizu. We are planning to release both phones in different markets until the end of the year. So we're kind of now narrowing down the product and working out on the last few details in order for us to be able to release it. So a couple of the challenges that we faced until this point. One of the big decisions that we took is to rebuild a new unit, a new interface, which is kind of a big deal. Because for us, one of the different things for us is that we're working on a distribution level. So we can't actually try to have something unique for the touch. We want to actually should do something more generic. And so it's kind of a big decision because it also affects desktops. Then one of the things that we do here, which is kind of also what Yola does, is reusing the Android BSP. I'm going to explain the details about and the decisions that we took in order to make that possible and why. Kind of giving an overall architecture of the system. Still, there's quite a more details that could fit on this presentation, but you can find it online or can ping me either in RCs and emails and so on, and just ping me on the card later on. And kind of trying to do like a little bit of more deep dive on some of the areas that we worked in for quite a few months and explaining the functionality in there. Some of the feature development that we still need to do in order to get the product out, and some more details for anyone that wants to get involved with the development. So, a little bit of the Ubuntu background, not just Touch itself, is until this point of the year, in the end of 2011, we were basically just targeting desktops and netbooks and that sort of thing. And then Mark came along with this idea to make it supported in more than those sort of devices and targets, but actually going for tablets, phones, and cars, and televisions, and that sort of thing. And one good thing for Ubuntu at that time, because it was quite well supported by different architectures, especially ARM, which ARM is kind of the most used nowadays for this sort of form factors. And we did also have some experience and trying to building different UIs in here. This is one kind of old. I'll give more details later on. And we were also kind of, with help from the community, trying to build this sort of things. And this was actually an Android laptop. It's called an AC100 running ARM. I think it was Tegra 3 or Tegra 2, I don't remember exactly. And but we were able to have Ubuntu running, and have it like Ubuntu images for it, and so on and so forth. So we kind of had already like pretty good support on the distribution side of it in different architectures and so on, which was an important thing to have at that point. And one of the requirements being a distro, as we are not a hardware company, is also, of course, make it supported by different devices out in the market. And then the first thing that you think, and that we thought at that time is, all right, we have here the laptop. We have a bunch of people using, and so on. But it's kind of a pretty complex design. Especially nowadays, it's kind of stable if you run Trusty, the 1404. Unity in itself is going to be kind of stable, way more stable than it was before. But the design itself is kind of a complex because you have, of course, you have X11, you have Compass, which is kind of a beast itself. Then you had Nux, which were our like toolkits, and we were mainly just supporting OpenGL in the desktop GL, not GLES, and we were as a normal distribution and normal desktop. We didn't have a way, we didn't optimize it enough for these other sorts of type of devices in here. So we had to step back a little bit and decide, okay, how can we actually create a stack or change the stack in a way to make it compatible for all these form factors? And which kind of leading to this goal in here, which where we are trying to go nowadays is having, of course, still making it well supported on the desktop, but having the same sort of UI, same sort of concept at least. Either it's a television, a tablet, a phone, or a car, or whatever that is. You could easily identify that it's, okay, this is running Ubuntu, this is kind of the same UI along the lines. Behaves differently, but it's kind of sharing the same stack in there, which is kind of an important thing because we want to make sure that the distribution itself is not that specialized in whatever factor that you're using. It's more like it runs everywhere. Everything here is just basically Ubuntu. It's even from the server, cloud, and so on, you have the same sort of stack in here. So on the, as I was saying, on the UI level, if you take a look on the desktop right now, it wasn't that ideal for us to continue extending that to make sure that we could have this sort of usage. And we had like as I said, we had like Compex, which was kind of complex, Nux, which was the toolkit that was decided and it was used, and it was pretty specific. Previously, I think it was mainly used for games, and it was pretty optimized, but it was quite complex to use as well. So it wasn't ideal if you wanted to have the flexibility to run all those sort of things and try to build it quickly. It wasn't the right one to use. And of course, we had X11, but we had like 2 projects coming along to kind of try to replace that. And so on that level, we were not that worried at that point. And from the interfaces that we did in the past, as was showing on the first slides in here, this was actually created using EFL. And we also had some experience later on with Unity 2D. I think if you use the 1204, I think it is precise. There's also an option to use the Unity 2D, which doesn't use the hardware acceleration doesn't use in GLES, and which is kind of fast. It's kind of basically the same interface in there. So we had some knowledge inside the company with different APIs and different toolkits in order to help us decide whatever we're going to use later on. And some of the experience that we had in there is that EFL itself was pretty fast, was small, was awesome for ARM devices. But we struggled quite frequently with the API. At that point, the alignment in EFL itself didn't have like this releases as they are having right now. Like they're doing like stables releases and so on. And at that point was kind of a nightmare. It was just basically a Git tree, everyone was pushing things around, breaking the APIs and causing a lot of damage. And the development tools and documentation weren't that great either. So, and on the other side, when we decided to build this using Qt, we actually had an awesome experience with it. At that point in time, Qt was already like starting to build KML, which is a declarative language that you can use to build interfaces. So it's not like using this old way of putting the widgets in place and the fixed size and so on, which helped quite a lot when doing the UI development. And development tools and documentation and so on were pretty awesome. Like it had the pretty good toolkit with SDK and so on. Because like we had a different company building those sort of things and a lot of people using, so it kind of make it easier for us to decide what we're going to use next. And so basically we decided, okay, if we want to go and make all those sorts of interfaces compatible with all those form factors, we need to build a new Unity and make it slim and fast, and which can work across all those different hardwares and requirements. And we decided to use Qt, and luckily with Qt 5, which is kind of a big step comparing with Qt 4, and brings KML in, brings like GL acceleration by default. So, and it is also like pretty compatible with OpenGL ES too, which was a big thing for us, especially on ARM. It had like different APIs and abstractions for all sorts of things that you can imagine, mostly because when Nokia bought Throwtech, they wanted to push Qt as their default framework all around the stack, and abstracting everything from multimedia, GPS, UI, and everything. So, which was a pretty good thing. And when you're actually trying to build, for example, with the Android, you have a specific set of APIs that can manage to do everything in a device. And Qt was kind of doing the same thing already, so which was awesome for us. The SDK itself was pretty good. I had a lot of developers using it, and would help us quite a bit thinking about convergence. Because as I said, we're not a specialized distro for mobile and this sort of thing. We actually want to make Ubuntu the baseline for everything that we use, either servers or clouds, and phones and tablet and so on. So we need to think about convergence because we don't want to fork Ubuntu internally and do our own thing in there. We need to make it in a way that is kind of generic enough to be used by these different requirements inside the company. But at that point, the only issue that we're struggling is finding hardware with decent drivers. And we had a pretty good experience, with pretty good relationship with Texas Instruments before actually they decided to jump off the game. And with Pentaboard mostly. That's why, like, before I actually went to Lenaro, I was working on the graphics stack on the Panda and doing some kernel development in there, and helping the SGX drivers be in place, GStreamers as well. So they had like a pretty good kind of a generic interface that would be compatible for what we needed. Like we had GStreamer, we have like an X11 based driver and so on, but that was mainly just Texas. Freescale also did this, did a little bit of that development, but it was pretty hard for them to support our requirements. And and at that point was kind of easy still, because we didn't have like Android. But later on, after like Android came along and took most of the market, was almost impossible to come up to the vendor and say, okay, can you do like an X11 driver for me? Can you do like a GStreamer compatible driver for me? And they can, nope. The only thing you can get is the Android BSP. So it was kind of a big deal for us. So we kind of knew what we need to do on the platform level, on the UI level, but okay, how can we cope with this sort of difficulties? And then kind of using the same architecture as done by Yola, and we decided to start to investigate how it would be doable for us to use the Android BSP. Because that was kind of basically the answer that we had from the vendors. They just have, luckily Android is using the kernel. The Linux kernel, of course, like is an old and ancient version nowadays, but it's still the Linux, and we could still work without many trouble with Ubuntu. But the BSP was kind of different. They had their own API, their own HAL. Everything was kind of specific, nothing generic enough when you were like thinking about the Linux stack, the traditional Linux stack. So how could we actually use those sort of things? And actually, the question is, can we? Could we at that point? If we could, it would be awesome, because we could solve, of course, not from the open source perspective, it would be kind of a big deal still, because we'll still be using, of course, proprietary drivers. But we could easily deliver our main goal, which is kind of doing an open source distribution and a solution for tablet and phones and so on, and still have users using a bunch of different hardwares, which then later on we could also try to look a little bit more in the closed source part of it, and try to, of course, convince vendors to maybe one day open that part specifically. So we thought this is kind of a pretty simple explanation about how Android actually works, and that they have, of course, the Linux kernel. They have like the hardware abstraction layer, with is a C and C++ layer, which with a pretty well-defined API nowadays, and which the vendors actually implement in order to support Android. And then, of course, we have all the big piece of Android, which is the Java layer, the GNI layer, and all the services and so on, which we didn't actually care. And we were mostly interested on having hardware acceleration and have sort of access to the kernel. So one of the issues then, when you look at it, trying to use the Android HAL is, of course, they use a different Libc, as we were seeing on the ELC presentation, and which is kind of complicated because not every single type is compatible, and they have like different implementations for the TLS specifically, for pthreads and so on and so forth. So it's not like one single like match both sides. And one of the issues as well is that besides, of course, like being directly connected with the kernel, so you can't necessarily, even nowadays, like you can't have, actually it's not common to have a vendor using a kernel that is not 3.4. They could, of course, use newer versions, but they are all like kind of stick in 3.4. And so if we wanted to use these BSP, we would also, as a consequence, be using this old kernel. And we would also be kind of stick with one specific version of Android, because while this API is well-defined for the vendor, not actually that important for the application developer, because he's just caring about the SDK API and so on. So this side kind of changes quite frequently, and we would need to select one version and try to go with it. So then it came along a project. We were looking internally on how we could actually match those and that goal and try to reuse some of the Android drivers. And luckily, it was pretty awesome that someone, Karsten, which I already knew personally before, when I was working in the INDT, which was a Nokia Research Institute, with the MIGO project and Maemo project, actually. And he came along and, okay, here's Libhybris, kind of an abstraction to try to use the Bionic-based binaries. And I was able to use the GLES drivers. So, okay, it's pretty cool. We were looking at the same time at the same thing. So let's take a better look and see how we could actually extend that and see if it could actually match our main goal, which would be to use the BSP itself, not only for the GLES drivers, but kind of extend for most of the important pieces there. And this was kind of explained already on previous talks. Libhybris itself is basically the Bionic linker. There's nothing really special in there. We just pick the source code of the Android linker, build it on the glibc side, and customize it a little bit just for us to being able to replace some of the symbols. So, for example, we have here a software, an executable, and that it goes through the normal GNU linker, and you have like this this is where all the kind of this magic happens here. We have a library called Libhybris Common, which basically contains the Android linker itself. And when the Android linker goes and tries to load and to find all the Android-specific libraries that SO is depending on specifically, it also, of course, loads and maps all the symbols internally. And at that point, we can hook and decide which symbol we're actually going to use, and if you're going to hook that symbol specifically and try to do some changes in there in case they are incompatible. So we basically have a table. I'll show a little bit of the code in there on the next slide, but we basically have a table that we can then decide if, okay, let's for example, a GLES-based driver is trying to use printf. So we could basically, okay, instead of trying to use the Bionic printf implementation, just take this one from glibc instead. And, or it could, of course, go and take the Bionic one, or it could directly go into the binary blob and use the binary blob implementation. And theoretically, this kind of works okay. Of course, as I said, we have some incompatibilities with some of the important components. The most complicated one in here is the way that Android treats, Bionic treats the thread local stores, and which is different from glibc, which is kind of a pain in the ass later on, because the way that it works in here, it tries to optimize it in a fixed table. So if you take a look at Bionic, there's a header file where it predefines a table of the predefined like TLS slots, and they have like specific functionality for each of the slots. Like one is the error code, one is the GL like hook table, and we had some other slots in there. And when you think on a glibc side, when you have like an application loading that symbol and trying to run something on the Bionic-based library, it would go and try to get to that table specifically, and of course then everything would be messy because glibc has a different way of treating that, and a different size and different area and so on. So it could create quite weird issues. Luckily on the ARM side of it, the way it goes, you also have like a predefined series of slots that is sequential. So we could, for example, fix on a specific slot that and also protect it from the glibc side that nobody would use, and then we could make it compatible somehow. But this got quite complicated when we also had to support x86, because x86 you had like a TLS block that then allocates like another TLS block, and then it links both together and goes on. And we could have like a simple list and kind of map the same way we did in ARM. So, but luckily, as one of the good side of it on the Bionic at least, the code is open source. We can try to narrow down the use cases of TLS in there and make sure that this is not used the way it is in Android. And of course, the pthreads implementation is a little bit different. It's way more simplified than glibc one. So we're going to see, if you take a look at the Libhybris code, most of the pthreads functions are actually hooked in Libhybris itself or directly going to glibc. So we don't use the pthread implementation from Bionic when using Android libraries. We also had another one that it is not here that I forgot to mention is, of course, if you see Ubuntu is built on ARM specifically, using ARM HF and not ARM HAL. And Android doesn't use ARM HF still. So we have that kind of issue in there, but luckily there was a macro that we could use from glibc that it could help us converting from floating point in there. So every time that you have a function on a symbol in Android using floating point, you can give it specify a macro that glibc will then wrap it up in a way that is compatible with ARM HAL and ARM HF, which worked great. And then we could still use the ARM HF system in Ubuntu and use ARM HAL-based libraries, which was great. This is trying to give a little bit more example of the code itself, how it works. This, if you take a look in the Libhybris project, this is basically the Android linker. There's no not a lot of changes in there. And you have like a function when it's actually reallocating the library and matching all the symbols. What it does is it basically gets the symbol name in here and call a function. This is basically the magic that happens in Libhybris. We basically, before actually going and taking the symbol from the library itself, we ask Libhybris if that symbol is mapped differently in Libhybris itself, or is going directly to use the glibc1 implementation. And if we don't have a hook specifically for that symbol, okay, it just go and grabs the bionic symbol and the bionic implementation. But in case we have a specific hook for it, it just go and use the Libhybris one. And on the table side of it, it's actually quite simple. You have like this hooks as .c file where I actually replace all the functions and that are programmatically and with our own implementation, or basically just tell them, okay, just use the one provided by glibc instead. And there's quite many functions in there, but the most complicated ones, of course, are the pthread ones. But once we were able to override most of that functions, we are kind of pretty good. We didn't have any other issue in there. So there's nothing actually really special. It was kind of a more like, let's try to go and try to use and see all the weird crashes that we got, and then we try to investigate and understand what was going on in there, and replacing each of the problematic symbol once we found them. So in case of have any questions, just feel free to ask anytime as well. So we got Libhybris to abstract the Android BSP, and but how we actually would use it in Ubuntu. And the way that we decided to do it is we could just use the BSP itself, just the Libhybris, and not have like Android running together with Ubuntu in the device. But the Android also provided a few useful core-based services that we could also use directly that would abstract a little bit more, that also would be useful for us. So what we decided to do instead is we basically compile a pretty simplified version of Android without any Java, Dalvik, and any sort of thing. Just basically the HAL and a few basic core services, especially the init system because of the property system in there. And we isolate it in a container. So if you take a look at Ubuntu Touch, the way it works, and as soon as it boots, it's open up and run a container with the very basic, like Android, the core of Android running in there. And then we have Libhybris to actually bridge both sides of it. And I'm going to show the picture how actually using it. And as I said, we use Libhybris to actually take usage of the symbols itself. And then, as I was saying previously, as we are kind of concerned with the desktop stack, with the generic Linux stack, one of the things that we had to do in Ubuntu Touch was, okay, we now have a way to access the BSP, right? We have it isolated in an ELC container, we have the Linux kernel. So how are we actually going to use it in our platform? So we started to look around and seeing all the major components that we were like using in the desktop already, which I'm going to give in more detail, for example, GStreamer. And okay, let's try to basically abstract and create a backend for those sort of projects. And then we don't actually need to show the Android-specific API to any of the applications that we have. We basically abstract in whatever other project that we were using and just create a backend for it in a way that we can still use the same major component, for example, GStreamer, in either the desktop or the Ubuntu phone. And for the application developer, it wouldn't actually matter. It's the same thing. So what did we basically did in there? And we created a platform API for Ubuntu Touch, which basically abstracts whatever Libhybris or Android-specific API in there, especially the sensor, GPS, multimedia. And okay, we basically decided, because if you think about it, we have like a Qt-based phone, but for games and so on, they're not necessarily going to use Qt. So we have to have the same sort of API, either Qt compatible or just like C, C++ compatible. So we kind of abstract that, creating our own platform API in there. On the graphics side, we had Mir, which was another project created by Canonical. But you could, for example, use Wayland as Yola is using, which basically abstracts the access to the OpenGLES drivers. And of course, the hardware composer, because we also want to take usage of that on Android. And on the Qt side, there's basically one component that we call as Qt Ubuntu. Because if you take a look in Qt, the way it works is you have all the access for the app developers, and you have the access for the platform developers. And you have like platform abstraction plugins that you can implement in Qt. And this is basically one of the plugins that we did, just kind of to tell Qt, okay, you are Ubuntu, and you basically behave this way, which tells them to use the platform API. And that then would go through Libhybris and so on. Kind of giving the big picture in here. And as I said, this is the container that we have running on Ubuntu. We have, of course, the Linux kernel. And we separate Android here, and we have like this bridge going over Libhybris. And we all abstract whatever kind of a platform-specific component, like, for example, GPS, multimedia, and so on, using the platform API. And we hook it in Qt using Qt Ubuntu. This is just some applications using Qt here. And whatever application that you had in Ubuntu, which is either like Qt or native applications, is just C and C++ without any Qt involved. It could just basically use the platform API, and we would then abstract it through Libhybris with whatever component from the Android BSP, or, for example, if you're in a desktop, we could just basically remove this entire thing in here and have like whatever other implementation that you wanted in there. So going a little bit in more details on some of the major developments that we did, and kind of shifting a little bit on telephony. There was a great talk right before this one, Martin, the work that was done for the Yola project, and which kind of connects with the work that we did here as well. But especially on the telephony side, we got it, okay, we were able to abstract the Android BSP, but we want to make a phone, right? How can we actually make it in a way that we can reuse the phone, the modem, by using whatever vendor hardware that they are providing? And of course, let's try to look in the Android BSP and see how we can use that. And one of the nice things that we notice in here is that it is pretty well abstracted in Android, and which helped us quite a bit. Here's kind of a very simplified explanation. Basically, you have the vendor library that implements then whatever like hackish way of access the modem and so on. Like, it doesn't actually matter for you when you're developing, but the vendor goes here and implements all their specific hacks and security, whatever. Like, because like modding, everyone thinks that they're special when they're developing their own modding, so they do whatever they want in here. And the way it works in Android, you have like a real daemon and a pretty well-defined kind of a protocol. There's a language in there for assisted and solicited and unsolicited messages that is well-defined in a header file. So, and luckily, which is pretty also kind of good for us, this entire communication goes through sockets, through a normal socket. So, okay, it makes it quite easy in here for you to basically cut it in here and replace it, everything in here. Just throw it out and use those, use basically the real daemon and the vendor implementation in there. And okay, so with that, we saw that there was a way to abstract the telephony stack. But which projects we would actually pick and try to implement the backend, which would then talk to Rio and do our modem specifically. And I don't think there are two projects when you think about the telephony service. The main one, of course, is Phono, and which is quite a well-matured project. And you also have like Modem Manager, I was talking on a previous talk. But Modem Manager itself, at least at the current point, is more like worrying about data connection and not voice and SIM Toolkit and those sort of things. So there's no other question, like it's basically a Phono. There's no way that you're going to use a different open source solution in there. So in the way that a Phono works, I don't know if this is because like they shared most of the BlueZ developers, also kernel developers and so on, but the code itself is pretty clean and easy to extend. You basically have all the core part of a Phono, and then you have different modem implementations that you can do, like kind of drivers in a Phono side. So okay, we just thought, let's just create a real modem driver that would then talk through socket and use whatever vendor specific modem that you have on the device. And it turns out that it worked pretty okay. We didn't have any major issues in there. There's some differences in the Phono API when comparing to Real, but we could easily just work around those without many issues in there. And as I said, one of the good things in here, the Libhybris are not even involved, so we didn't have to worry about any sort of incompatibility between Bionic and so on. And on the connectivity side and data side, we had Network Manager for desktop. Everyone that uses Ubuntu or use it for the previous, I don't know, like 10 releases. And you all know that we use Network Manager by default. And we got at that point, and if you take a look in a Phono project, it basically tells you, okay, if you want to use a Phono and you want actually to manage the network and so on, there's already a product that kind of shares most of the developers between the Phono project as well, which is called Command, which was created by Marcel as well. And I think Yola uses Command, right? And on the good side of it, like on our project, because everything that we do is open source, like most of the decisions that we do, that happens like through the open. There's no like secret magic happening there. And we came basically, okay, we're now having the virtual UDS, which is basically like, I think every 3 months, that I have this sort of sessions, but happening through Google Hangouts. And where it basically decides all the technologies that we're going to use. And which was, in this one, it was actually a pretty fun one. We got Marcel, we got the maintainer for Network Manager as well, and okay, and both in the same session, okay, let's try to decide here which stack we're going to use. And each one of them had their own pros and cons, but the kind of the decision that we took was mostly because we don't want to break the desktop. We all know the Network Manager kind of works in the desktop, and it is pretty important for the servers. And the Command is mostly just worried about like mobile at that point, specifically for mobile. So we didn't want to create, it's kind of a nightmare for anyone that is using the desktop. So okay, let's continue using Network Manager in there. But the problem in there is that Network Managers talks with Modem Manager, not with the Phono. There wasn't any API to talk with the Phono at that point. So okay, let's go and create another plugin for Network Manager to talk with the Phono, and we're going to solve this issue, and which we currently already have. So every time that you use Ubuntu Phone to set up the data connection, like Phono set up the data connection through Real, and then talks to Network Manager to get the IP and so on and so forth. On the Bluetooth side, there's no special requirement there. You had like BlueZ, which works great. There's no specific issue. We kind of use the 4. Still, the 5 brings some other dependencies that we need to be more careful. And on the communication framework, we also use Telepathy, bringing a Telepathy Phono project. Telepathy is basically, let me see here. Telepathy is basically a way for you to communicate with whatever communication protocol that you want, either like gTalk, Jabber, whatever protocol that you're deciding in there. So we basically created, not created, but used a project I think Nokia actually created a few years ago, which is Telepathy Phono. So you could have a messaging application that could talk with either the common user protocols and also send an SMS and do voice calls and so on, and which is a pretty generic and nice interface in there. So kind of in the big picture, what you see here is you have like a funnel in the center of it. We have our real daemon in here, which goes through socket and talk with the real daemon, which is basically running in the Android container, and which then talks with network manager to set up. Of course, everything here uses VBus to set up the data connection, and for BlueZ, it was already well integrated in the funnel. And for anyone that uses this sort of interface and the modem and so on, we just have telepathy. So this is kind of the big picture in there. One of the nice things that was kind of pretty, as was presented by Marty on a previous session in here, we kind of shared the development. Like we created the project, and then they came along and, okay, we find that it's pretty good. We want also to go and use the same solution. So they extended and fixed quite a few things in there, and we're grateful for all the work that they've done. And which is one of the awesome things about doing everything in open. Now, I'm going to talk a little bit more of multimedia and how we actually did, because multimedia is also one of the big major pain in the ass like frameworks, and which also like every vendor thinks that they're special somehow in there and creates their own like weirdness and so on. So if you want to create some kind of a generic abstraction, there's no much other solutions. There, of course, like VLC uses their own like solution, but if you want to be compatible with most of the applications that are there, you're probably going to use GStreamer. There are no like, there are other solutions, but GStreamer is kind of the most common one, and which is kind of used by quite a lot of components. Like WebKit was using it, of course, Qt WebKit, and Qt Multimedia, which was also like one of the components in Qt, and we also have like many other components and projects using it already. And it's good because it also supports a wide range of plugins, like it can decode and encode and handle different formats and so on. And it's pretty well known and also quite an old project. And one of the nice things in here is that they already kind of had some sort of abstraction for Android, because they also wanted to run GStreamer inside Android and not to use any of the multimedia players and so on that Android uses, but they also wanted to use the hardware decoders that are already there, available in the BSP. So they basically decided to, instead of using the service itself, just go directly to the media codec API and abstract on top of the GNI layer. So, for example, if you want to use GStreamer in Android, it basically has like some special components that talks with Android over this GNI layer, and you can have like harder accelerated video decoding and audio and so on. And which was kind of a big thing for us because this is actually one of the low parts of the low stack of the multimedia side of Android, and we could just basically abstract on top of this guy as well. But we don't use Java, we don't use GNI, we don't use anything that is this sort of Android specific. We wanted like a pure simple C, simple plus basic API. So what we did in here is basically kind of mimic and kind of copy most of the logic that was applied on top of the GNI layer, and but instead on top of stage fright directly and Libmedia using the media codec in here, but talking through C and C++. And because we have like Bionic-based libraries, we use Libhybris to actually do the bridging here. And we can get pretty nicely running and so on, doing texture streaming. So we kind of saw this big part of it as well. So if you take a look in the Ubuntu Touch, and you're going to see that there's an element in there on GStreamer, which is called the Android media, that depending on, of course, the BSP that you have, you're going to export some GStreamer elements in here that of course could decode whatever the Android decodes as well, like through hardware, either like H.263, MPEG-4, AVC, and so on and so forth. And then, of course, knowing GStreamer, you could either like use the pipeline. You can write a pipeline in hand, and or you can just let GStreamer itself to handle that and find it for you, as long as you have, of course, all the interfaces for and everything that your plugin implements and so on. Which is nice because then we could, here, for example, it's a pretty simple way of decoding through hardware and pushing to a file in a raw format in there. We basically just have like the H.264 ports, and then we have like this element. And here's kind of where all the magic goes. Like it talks with Android using the media codec API that then talks with OpenMax interfaces that they have and do everything by hardware. In the end, what you get is basically a texture. And here you could replace the sync with whatever GLES compatible sync that you might have, which is there's an EGL sync and whatever. We kind of, I think we have one that is specific to us, mostly because of Mir, which is called a Mir sync, but there's not much specifics in there, because on the EGL sync now, if you take a look on the GStreamer code, there's some X11 specifics in there which we don't actually use. So we had some meaner and simpler sync for us. And also, this is kind of the big picture that we have. We kind of changed this a little bit. Yesterday, we just landed a project that is called like Media Hub, which basically abstract, like we now have in Touch the latest image. You have like a service that handles media, and that actually is the one that talks with GStreamer. But until yesterday, what you would get is you have like whatever components that want to talk with multimedia, either like WebKit and Media Scanner that generates the thumbnailing, and Qt Multimedia, because here, for example, anyone that is using and writing a KML-based multimedia application would go through Qt Multimedia, which would then use GStreamer 1.0, is actually the 1.2 version that we're using, would go through our Android media-specific element, which then talks to Libhybris and do everything on the Android side in here. And the good thing about GStreamer is that we don't actually need to care about audio in here. We don't use the audio flinger service from the Android side. We just basically use pretty simple pulse audio, and which works great. We didn't have any sort of sync issues and so on when doing this implementation. It worked pretty nicely actually, and you can have like software decode whatever device that you have the working Android BSP. In our case, any of the Nexus devices, Nexus 7, 4, 5, 10, and so on. And showing a little bit like a different implementation in here is, okay, we now have we have telephony, we have GLES, we have the display support, and how we're actually going to use camera in there. Camera is kind of complicated in Android. Like, they have, either on the HAL side, they had so many different HALs in there, like, and the ones that are incompatible with each other, like with API breakage, API difference, and so on. So it's kind of hard for us to abstract on top of that side, and that thing specifically, because we need each device supports one of the HAL versions, so we will need to actually handle a lot of different like specifics in there. And yeah, as this, I think it is the last slide in here. So basically what we did in here is, as it's pretty hard to abstract in here, we just kind of, okay, let's decide to, as we have the container, let's use the camera service for an Android, which is pretty simple and not actually connected with multimedia audio and so on. So we just basically implemented a Qt plugin that goes over Libhybris and talk with the camera service, and then we could have the camera working. Pretty simple, like it was. We could done in like a couple of weeks. So here's some of the things that we're working on. We have like hardware decode. We're working on now for video encode support, which we currently don't have. and so we can enable video recording, but we're also going to land support for MMS and working on BlueZ nowadays. And as I said, like, get in touch. Everything that we do in here is open. You have like, we are hanging around an Ubuntu Touch, a free Node RC channel. There's a mailing list in here where people publish daily updates and whatever that is landing on the images. And you can flash these images there. Everything is public. And you can also come to the virtual UDSs where we decide whatever we're going to do in the project and in the future milestones. Well, that's basically it. Any question? I think we don't have many minutes, but you can just like come here or get me in the corridor in here, and we can talk. Yeah. Yeah. Right. That's it. Thank you very much.